material properties, loading conditions, environmental conditions, and surface conditions. Different parameters are there. Here, actually, I'm concentrating on this environmental conditions. So in these environmental conditions, temperature is the major factor actually. So because this temperature basically changes its both mechanical properties and the chemical properties of any material. Here, this temperature, when we consider temperature parameters, there are two types. One is temperature from ambient, like surrounding temperature. Consideration of surrounding temperature is important, and also in friction process itself, because of friction, internal temperature generation also will be there. Here in this lecture, I am going to concentrate this internal frictional heat actually, because of friction, the produced heat. How we can find out how much heat has produced at the contact surface? I'm going to find out from inverse heat transfer method actually. Okay, so here actually types of frictions. This is also important. Coefficient of friction depending upon types of frictions also. So there are different types of frictions: static friction, sliding friction, rolling friction. Different types are there. So actually, in this lecture, I'm going to concentrate on sliding friction only. So this application oriented, when we see the friction applications actually in offshore platforms or any framed structures, if you see the effect of loading, like lateral loading, earthquake loading, different wind loading, different kind of loadings we can reduce by providing different kind of dampers. Friction dampers are one among them actually. So here the efficiency of the damper depends upon coefficient of friction of the material, the pad materials what we are using. So we tried in our studies with the aluminum pads actually, both the pads, aluminum pads, like two surfaces we made with aluminum, but we have not made a prototype. Whatever I am showing here, we have not made, just using the available experimental facilities, we measure the coefficient of friction actually. So this is one of the applications, and other applications if you see disc, like brake disc arrangements, there also the coefficient of friction, study of coefficient of frictions are very important. And one more thing is engine piston, cylinder piston arrangement, like where the sliding happens, there also this coefficient of friction is more predominant actually. Like that depends actually. Some cases we need coefficient of friction, some cases we don't need coefficient of friction. See, in this brake arrangement we need actually coefficient of friction, but in this cylinder kind of things we don't need coefficient of friction, we need a smooth contact actually. So here, to study these kind of friction properties, we have to follow depending upon the applications. Like if you see ball bearings, so bearings also different bearings are there. Spherical bearings, like the balls, spherical type of balls, and the cylindrical type of balls. Depending upon the type of applications, we have to choose the equipment. Which type of equipments? Here from the literature, I have taken some different type of equipments, rolling friction to test this A type, whatever I have given here. This is the rolling type of contacts, to study the rolling type of contact. One more thing is block on ring type of friction. Like this, different kind of things actually. Experimental facilities are available. So in our studies, what we have taken this experimental sample, I will show in further slides actually. Here, the main aim of this presentation actually, objective of presentation is to estimate the frictional heat using inverse heat transfer method. And one more thing is effect of the loading parameters, like normal load. Already I have told coefficient of friction depending upon loading and sliding speeds and the different parameters. Normal load, here in this presentation, I am going to discuss about normal load, sliding speed. How these parameters affect the frictional heat, I'm going to explain in this study. More of the presentation is concentrate on estimation of this frictional heat actually. So before going to the study, any study, we have to confirm the materials what we have taken is proper. Like we have considered the L6061 E6Li, but in metallurgical point of view, in mechanical point of view, before going for any study, we have to confirm that material is L6061 T6. This is authenticated proof. We can check any material by X-ray diffraction methods and EDS analysis actually. So these two are similar kind of things, but application is different. This X-ray diffraction methods, from this X-ray diffraction methods, we can find out the phase of the material. So something like aluminum, maybe in the form of aluminum oxides, aluminum nitrate, something like that. We can identify the phase of the material. Here, actually, this graph, X-ray diffraction method, from the X-ray diffraction, whatever the graph we plotted here, it is intensity versus 2 theta, phase angle actually. for each element, any element, aluminum or oxygen, for each element at particular angle only it gives its maximum intensity actually. For aluminum, that angle is this 2 theta value, it is around 37 degrees centigrade. So, sorry, 37 degrees angle actually. So, the 37 degrees we have observed, like other phases also we have observed minor aluminum, but more intensity we have observed at 37 degrees only. So, from that we can say this is one of the proof the considered material contains maximum aluminum. Okay. And one more thing is from EDS analysis. This is from semi-analysis. Semi-analysis both for metallurgical people and civil people also will use. Here from the semi-analysis, EDS is the one of the module in scanning electron microscope. From the EDS, actually, we can find out which are the elements present in the basic elements present in the actually. So here I have considered only four elements only I have observed. Why? Because this aluminum 6061 contains maximum aluminum, magnesium, and silicon. So that's why I have checked the major components only in this one. But unfortunately, we have observed oxygen also. Generally, oxygen will not be there. Pure Al6061, if you take, it won't contain oxygen actually. But why we have observed oxygen here, but any material which is exposed to the environment, automatically it goes to oxidation process, some amount, minor amount, definitely it go to oxidation process. That's why we have observed here oxygen also, some minimum content. We can't avoid that thing if it exposed to environment actually. If it is not exposed to environment, if vacuum the chamber somewhere, if you maintain, we can rectify this problem, oxygen content, anything. So this is how we have confirmed the material is aluminum 6061 and major most of the content is aluminum. So later the specimen preparation, we have purchased actually one cylinder, aluminum cylinder we have purchased. From that one, distant pin specimens we have made for the experiments, and size of this distant pin specimens will depending upon the equipment what we are using actually. The make of the equipment company, that depends upon the company. So here in this study, we have used 160 mm diameter disc specimen. This is the disc specimen, 8 mm thick. That is the specifications the company people, the equipment company people, what they have given according to the specifications we made. And the pin specimens I have given in a magnified way actually. This pin specimen length is actually 30 mm length, total length, including this curvature. Here actually we want to create one cylinder on flat contact type. That's why one portion, like one side of the pin, we made a cylindrical portion with 6 mm diameter or 3 mm radius. Radius of curvature at this portion is actually 6 mm radius, and other longitudinal directions, like other direction, this is 6 mm contact, actually line contact. So this is the specimen details what we have considered, and this is the experimental setup what we have pin on this. This is called a pin on disc experimental setup. Initially, I have showed different type of experimental setup. This is one among them actually. So while conducting, you can observe here the wear crack also because of this friction process, and have given the schematic of the specimens. I arranged the specimens inside, and here you can observe the thermocouple. So these thermocouples we have used to measure the temperature. We have measured temperature 3 mm and 7 mm from the contact surface actually. I will show schematic representation also in the later slides. Here, the right side of the figure, this is related to high temperatures. In this lecture, I am not going to cover about high temperature experiments basically. Experimental conditions what we have used for this study is 1 kg, 1.5 kg, 2 kg. 3 different normal loads we have considered, and 3 different sliding speeds. Just we want to check how this frictional heat is behaving with respect to the different experimental conditions. And temperature we have maintained room temperature, okay? And at room temperature we have conducted the experiments. Anyway, from the thermocouples we got the temperatures also before conducting the experiments. So from those temperatures only we have fixed 30 plus or minus 1. It is varying actually. So, and before conducting the experiments, we should confirm the contact what we have given, it is within the elastic limit actually. The intention is that before starting the experiments, the contact should not go into plastic state. So that's why for the cylinder on flat contact, what we are using this like in the study is the cylinder on flat contact. For the cylinder on flat contact, maximum pressure, here I am showing A, 1 point I am showing. So at this point, we'll be having maximum pressure actually, okay? So the maximum stress or pressure, that maximum stress we can find out using the Hedgen contact formula. Hedgen is a scientist who found out stress at a point, like the maximum stress for different configurations, flat on flat, flat on cylinder, cylinder on cylinder, cylinder in cylinder. What are the possible conditions? Because of these geometrical changes, he has made different formulas. This formula is only for cylinder and flat contact only. From this formula, we have observed the stress at the contact position before starting the experiment. It is well below the yield strength. Actually, the yield strength of aluminum, it is 270, approximately it will be equal to 270 megapascal. So the pressure what we have observed from this formula is at 1 kg 82 megapascal, at 1.5 kg 100 megapascal, at 2 kg 116, almost 160 megapascal actually. That is, if you compare with the yield strength, that is for all the experimental conditions what we have considered, it is almost less than the 50% of the yield strength. So almost it is safe. We are not, it is not equal to the yield strength of the material. So all the experimental conditions what we have considered, it is under the elastic limit. So for this frictional heat estimation, this is the flow chart what we have followed actually. This is abstract of the study, basically, if I want to say. So from the experimental conditions, like whatever they mentioned in previous slides, from the experiments, we have observed the temperature at, just I want to draw and show here. So if it is a pin specimen, so we have observed temperature at this, like at 3 mm. I think not exactly. Yeah, 3 mm. At 3 mm we have measured. 3 mm is from the bottom, from the contact surface. I am saying at 3 mm we have observed actually temperature, and again at 7 mm also. At 2 points actually we have observed temperature. Okay. From these temperatures, we want to interpolate the temperature at this contact surface. Why? Because we can't arrange any thermocouple at this contact surface because of friction process, it may damage actually. So we can't arrange any thermocouple here. That's why from other location away from the required point, we are interested point, we are arranging two thermocouples. From those thermocouples, we are interpolating like what will be the temperature at the contact surface. So input data for this one is the temperature measured at 3 mm and 7 mm, and some algorithm you have to follow to from this known temperatures to unknown temperatures we want to find out. That is finite element methods we have used actually, and Beck's algorithm I have used. I will explain about this finite element and Beck's algorithm in further slides. From using this Beck's algorithm finite element analysis on the input data, that what is the input data, 7 mm and at 7 mm and 3 mm measured temperatures. We have written MATLAB coding for inverse heat transfer method. From this inverse heat transfer model, we will get heat flux at this contact. So here everyone should know about the heat flux. What is heat flux actually? So if you take the contact surface, just this bottom portion I am drawing, at this contact surface, because of this friction process, some heat will generate. That heat will be flowing. Okay, all the directions it will be flowing. Just I am assuming it will be flowing upside. So when the heat is flowing, the amount of energy passing through an area per second. Okay, per second we will say that one as the heat flux. Heat flux actually, the amount of energy passing through an area, unit area, it is called heat flux basically. That heat flux values will not be, we can't measure at this position. So from this inverse heat transfer model, we can estimate the heat flux values and temperature at different points. We have measured only at 3 mm and 7 mm. But wherever you want along the length of the specimen, wherever you want, you can calculate from this inverse heat transfer model what I have used. So the output of this inverse heat transfer model from the MATLAB coding what we have derived is heat flux values at the contact one and temperatures at each position, something like 1 mm, at 1 mm, 2 mm, 3 mm, 4 mm. 3 mm already we are having, okay? There no need to bother. At 4 mm, 5 mm, at different positions, at required positions, we can calculate, we can get the temperature data. So these two values we can get output from the inverse heat transfer model what we have written. And later we want to check this inverse heat transfer model using some known package. So ANSYS, we have used another numerical package actually. So this will also depending upon the like background of this ANSYS is finite element methods only actually. So in ANSYS, like we have used the thermal models we have used actually. Transient thermal analysis we have used. In the thermal analysis input what we have given, the heat flux what we got from this inverse heat transfer model, what we have calculated, heat flux we have given, and the temperature 7 mm, uh, 7 mm we have given, right? The temperatures we have given actually. We have to give end conditions for the ANSYS analysis. That's why at 7 mm, what we have measured, we have given as the input values, and we find out the temperature at all. Again, in this ANSYS analysis also, we have find out temperature at each point, like 1 mm, 2 mm, 3 mm, 4 mm, all the points we have measured. And we compared both the temperatures, like inverse heat transfer methods, whatever the temperatures we got, and ANSYS, from the ANSYS temperature distribution all along the length of the specimens, whatever we got, we have compared, and we have concluded both are coming almost same actually. From that one, we have concluded the method what we are following is correct actually. So while measuring the temperatures, this is the experimental setup. This is the data equation system to measure the temperature actually. So these lines, whatever you are seeing, these wires are actually thermocouple wires actually. So here, if you see magnified way I have given, so at above the top of the contact actually at 3 mm, one thermocouple we have arranged. In other way, in the perpendicular to other side, another thermocouple is there. That wire only here, what I have given actually. From this two wires at 3 mm and 7 mm, we have measured temperature. Here in this schematic view, you can see exactly where we are measuring temperatures. In this pin, if you see in different directions, one direction looks like flat contact, but that is not flat actually, that is a line contact. And other directions looks like the cylinder contact actually. Here you can see this curvature easily. So at one side, we were unable to arrange these thermocouples into one phase. That's why in two phases, two perpendicular phases, we have arranged at 3 mm one thermocouples, you can see here. At 7 mm thermocouples, you can see here actually. So these thermocouples generally diameter, like minimum diameter, we will get 1.5 mm diameter. So the drill bit we have used for the arranging the thermocouples are 1.8 mm drill bit actually. We have drilled the specimens till the center of the specimen actually. So in both the cases, if you observe properly, till the center of the specimen, like we have drilled, we want to measure the temperature at the center of the specimen actually. So here, these are the properties. And one more thing, here we have considered two materials. Like why I have considered the two materials, these two materials are having two different thermal conductivity values actually. So aluminum is having 167 thermal conductivity, SS304 16 point. If there is some huge difference in thermal conductivity, how our model is varying, we want to check actually. So some finite difference models generally, there are some faults actually. When this thermal conductivity changes drastically, the estimation methods goes wrong. That's why from the literature I have observed, I have not done any experiments on that one. From the literature I am saying, so that's why we have used finite element method for this particular case, and we tried the same thing what other researcher has tried, and we got succeeded actually. So here you can see the first figure, the measured temperatures at 7 mm and 3 mm. This is at red line is the 7 mm actually, at 3 mm black line is the 3 mm for SS304 Li. And other Li, AL60626 Li, here are the temperatures, measured temperatures at respective positions, 3 mm and 7 mm positions actually. These are the input values. In that before algorithm what I have given, the input temperatures, these two temperatures have I used as input values, and later I have used the finite element method actually. So this is the governing equations what I have used for this finite element model. These governing equations using different methods, Galkin's methods or Rayleigh's methods. There are different methods to convert into finite element formulation actually. So before converting to finite element formulation, we should know what are the initial conditions and boundary conditions actually. So initial conditions, the particular problem, whatever they are taking is time dependent, we will get initial conditions actually. Otherwise, when the particular problem is the static analysis, we will get only boundary conditions actually. So here initial conditions what I have used here here t x comma 0 I have mentioned actually. X is the space component. Space is something like if you assume this is the pin specimen. So from this point, from this contact point, this is the X actually. At each point, interested, where we are measuring. So at any x, at a second point is time is actually at any time. Sorry, at 0th time. Okay, initial. This is the initial conditions at 0th time at any point of space. At any point of space means in the spin at any point actually. What is the temperature? We have to give as an input for this model. So that model, how we can find out approximately we can't give actually. So anyway, at 3 mm and 7 mm we are measuring. Actually, at 3 mm we are measuring. At 7 mm we are measuring temperatures. At this 3 mm at 0th time actually. Okay, initially what is the temperature? That temperature I have assigned for entire specimen length. For this entire specimen length, initial time I have assigned at 3 mm what I have measured. And heat flux, amount of heat energy at that heat flux also where it will be there actually input heat flux at contact only it will be there. That's why here x I have not given, only at 0, and x is equal to 0 actually. So at this contact position at time 0, when the time 0 heat flux is 0. When time 0 means when it is about to start the experiments, when the pin is about to slide at that time actually heat flux will be 0. There will not be any heat flux. After starting this friction process, only heat flux will generate generally. That's why I have taken 0 heat flux at 0th time actually. These are the initial conditions and boundary conditions. If we take actually at x is equal to 7. So boundary conditions here for this finite element model, I have not considered the entire length of the spin. Entire length of the pin is 30 mm, right? Actually, so this 30 mm length I have not considered. I have considered only 7 mm actually. So till the position where I have measured the temperature, this within this 7 mm only I have analyzed. Okay, so within this 7 mm, at the 7th mm, okay, at the 7th mm, whatever the temperature what we have measured, we are giving. This is the boundary conditions. Okay, this boundary conditions values at 7th mm at any point of time. So here, if you observe these input values for different points of time actually, till 600 seconds we have measured actually temperatures. So first second, second, third second, whatever the temperatures we have observed at 7th mm location, we are assigning as a boundary conditions. Heat flux at x is equal to 0 and time t at any point of time. When time progresses actually, heat flux will keep on generating. So that particular heat flux, okay, with respect to the time, how much it is there, we are assigning. These are the boundary conditions actually. Boundary means at initial point and final point. Okay, at this initial point heat flux we are giving, at the final point the known temperature we are giving. Something like we are forcing at 7th mm at any cost the temperature should not be increased, the measured value, like that we are forcing to the model. This is what we are doing actually here. So and later what I already have told, this governing equations we can convert it to finite element model actually. So while deriving this finite element model, actually we have used for the space finite element concept, and for the time, like when time progress from first temperature at t is equal to 1 at 1 second, at a t is equal to 2 while you are estimating, at a t is equal to 1, whatever the temperatures we have estimated, we have to give input to the t is equal to 2 actually 2 seconds at this 2 seconds when you are measuring. So that's why while going for this time dependent, like for next second what is the temperatures when you are estimating, we have used finite difference model. It is not purely finite element model. Both finite element and finite difference, both the things we have used actually in this model. So this is the algorithm what we have used to write the MATLAB programming actually. Here I want to mention the assumptions what we have made while analyzing this thing. So this is the pin specimen. If you take only the center span, like center plane, so ABCD. So if you want to understand, okay. So this ABCD plane, whatever the central plane it is there, that plane we have analyzed. So the assumption is something like temperature is flowing from the center point actually. So actual case it will not occur. It will pass in all the directions actually temperatures. To simplify our model, we have assumed like this: it is flowing in vertical directions and only this plane. In this plane, it is flowing actually at the middle plane. That is why initially I have showed the specimens also we have drilled till the center point actually. We want to measure temperature on this ABCD plane only. So this plane only nodal points I am for magnifying way I have given at each mm, 1 mm at like nodes I have measured, indicated here actually. First node, second node, 7 mm, right? 7 mm means we'll get 8 nodes we'll get from bottom to top actually. So at fourth node, that is fourth node means that is at 3 mm. Fourth node we have measured temperature, at seventh node we have measured the temperature. And heat flux, whatever the frictional heat flux, whatever we are giving inside, okay, that is at this contact, at the face of DC actually, okay. So if we can understand this model, further it will be easy to understand actually. So while starting the algorithm, actually initial heat flux, okay, at a t is equal to 0, initial heat flux we are giving 0, and all other at I is the position actually. Ti, what I am mentioning, I is the position, space actually. All the space, initially I have mentioned in previous slide itself actually, boundary conditions, okay. Initial conditions, those conditions we are giving actually in this position. And next to some conditions I have given n is equal to greater than n max. N is the time step actually. Like depending upon here, for 600 seconds I have measured, but the data what we have acquired per second, 5 samples we have acquired actually. So 5 into 600, those many time steps you will get actually by analyzing this particular problem. So if time is maximum, last time step reached, it has to stop. This algorithm has to stop. If it is less than the last time step, it has to go to next step actually. This is the procedure what we have followed. And initial step, if you see here, assume the heat flux constant. So here actually process is heat flux, whatever frictional heat flux, we don't know. We have not measured anything, and actual heat flux, how much it is there, we don't know exactly, whatever at the contact position. We have to assume some dummy value we have to assume here actually. So that dummy value, what I have assumed, it is increasing from 1, okay, basically, okay. So heat flux value 1 I have started, and in this algorithm what it goes for this heat flux, suppose at the first second I am assume heat flux is 1, heat flux I am representing with Q is equal to 1, I am assuming. Because of this heat flux, heat will flow, this energy will flow along the length of the specimen, okay. When it is flowing, definitely at all the points there will be some change in temperatures. At fourth node, at say 8th node, at all the points there will be some change in temperature actually. That temperature we are measuring, okay. So from the measuring temperature, we are again correcting this heat flux what we are assuming. How we are going to correct, I will say now here actually. So this inverse heat transfer method, basically it works only for the parameters which are dependent. So the temperature what we are measuring at fourth node and 8th node, and this heat flux are interrelated. When heat flux increases, actually the temperatures we are measuring, what we are measuring will increase actually, dependent parameters. When these two dependent parameters, relation, when there is a relation between two parameters, okay, when two parameters are dependent, the change in one parameter, okay, here the known parameter is temperature, okay, the change in one parameter, from that value we can find out the change in other parameter. So this is the concept here actually. So we have measured the temperatures. From these temperatures we can estimate the heat flux, okay. So initial step we are assuming some heat flux, and we are estimating the temperatures at different nodes at the 3 different particular, at 4th mm is the 3 mm temperatures. At the 3 mm, what is the temperature actually. So here further steps, if we go, estimate the temperatures at different nodes using equation 3. Equation 3 is what I have shown here. From these finite element formulations, we can estimate temperatures, all the temperatures we can estimate. Calculate the sensitivity quotient using equation 4. Equation 4 I have measured, mentioned here, you can see. So this phi is the sensitivity quotient actually. So when there is a small change in temperatures, okay, and heat flux actually, when there is small change in heat flux, and how this temperature is changing, okay, the relation between temperature and heat flux, here we are deriving.
Excuse me, sir. Sir,
Please tell,
we
sir.
are running out of time, sir. Sir, please, can you come to
Okay.
the important
Uh,
point, sir?
okay, sir. Okay, sir. Then I will conclude. So, like this, from the dependent parameters, we can find out the temperatures at the unknown areas. So, using this measured temperatures at 4, 3 mm and 7th mm, we have calculated the heat flux at the contact area actually. From those heat flux, we can find out the temperatures at different nodes, first node, second node, all the nodes. All the nodes means something like at the first 1 mm, second mm, third mm, from the contact surface. These are the measured, like calculated temperatures. They are not measured temperatures, but two different materials and heat flux values, whatever things are there. And these things we have validated using finite element model actually. While going for finite element model also, what are the assumptions we made? Both the things, those same assumptions we followed for finite element model also. Purely this analysis based upon the conduction only, not on convection process. That's why two phases, adjacent phases, we have taken as insulated phases, so that there will not be heat loss. There will not be any heat loss from the specimen actually. So from this one also, we have compared the results from the finite element results and the what we have observed. The error, difference between the MATLAB coding what we have written in finite element method, it is very less. It is something like mean value. If we take this mean value, it is falling around 0.05 degrees centigrade for the both the cases, like for both the materials actually. So later we have applied this thing for different experimental conditions, like what I have mentioned, 1 kg, 1.5 kg, and 2 kg for all the experiments. These are the measured temperatures at 3 mm and 7 mm. From these measured temperatures, we have estimated the heat flux values, and later we find out the temperatures at different locations actually. These temperatures at surface, we are interested in surface temperature, how much temperature it is there. So this is the summary of the temperatures, surface temperatures. Why we are studying the surface temperatures? Depending upon the surface temperatures, only material property will change. We generally aluminum at around 100 degrees centigrade change to aluminum oxide actually. That's why we want to study how much temperature is there at room temperature. While at room temperature, where it is sliding at different conditions, what we have considered at different speeds and different normal loads. Like here what we have observed, quantified, we have quantified how much temperature it is coming at 1 kg to 2 kg normal loads, and we have observed when normal load and sliding speed is more. So here we have observed around 100 degrees temperatures, like temperature, frictional heat, it is increased to almost 100 degrees centigrade. So these are the references what we have followed for this work, and thank you for the patient listening. So any queries, please you can discuss.
I request the participants to please raise the queries if you have.
Srinivas Reddy sir. So,
Please sir.
is there any possibilities to give the sound evidence for your I mean like modeling? Is there any possibility to do experimental thing?
So actually, yes, sir. It is there. This possibility is there. Actually, this process what I have used is a cheaper process. Actually, like with low cost, we can do something like infrared cameras are available. We can measure the temperature, but using those infrared cameras also, we can measure only the surface temperatures. We can't measure the inside the pin how much temperature is there. Only the on the surface how much temperature is there we can measure from the infrared cameras. But it is very costly process, that is.
Okay.
Any some more? I mean, any more questions, please, participants? Participants, any queries? Sir, Srinivas,
Yes,
we
sir.
thank you. We thank you for your continuous presentation and informative presentation on behalf of Center for Research and Innovation, KSRM College of Engineering. So we
Thank you,
expect
sir.
such type of presentation in future also from
Thank you,
various
sir.
departments of KSRM College of Engineering. I thank
Okay.
all the participants of today's lecture series. So we'll meet once again in the tomorrow's lecture series. Thank you one and for
Oh,
attending today's lecture. Thank you.
oh, thank you, sir. Thank you for
We
attending all the people.
yes, sir. We
Oh,
can leave now.
okay.